Alright, welcome to a review video for Infinite Series. Just wanted to do a few examples for you here, giving you the general idea of, what the series looks like, whether it converges or diverges, and then what test we would use. So just getting you started on lots of different types of series. So these come from the chapter review questions at the end of the chapter. So they've got about a dozen of them. So let's dig in and take a look. So here we've got a sum of n over n cubed plus 1. These are both polynomials here, so I'm looking at dominant terms. And I see that this thing is approximately equal to n over n cubed, which is sum of 1 over n squared if you cancel. And this is a p-series, and it converges by the p-test because 2 is greater than 1. So I look at this and I think it converges, and since, dominant terms, it looks like a 1 over n squared, I think that we should do a limit comparison. We could do a direct comparison too. Because a direct comparison, we want to make it smaller than a series that converges, because we think it converges. So we could just take that 1 away in the denominator. So actually here, we could do a limit comparison, certainly. But it's actually easier here to do a regular comparison here. Actually, n over n cubed plus 1. We want to overestimate. It's going to be less than or equal to. We're going to decrease the denominator. That'll make it bigger. So n over n cubed, which equals 1 over n squared. So if we did a limit compare with these guys, we actually would get 1 for an answer, which means that these are essentially the same in the limit. But here, we've actually shown that 1 over n squared is bigger than n over n cubed plus 1. Since this series converges by a p-test, so we'd say, sum 1 over n squared converges by p-test. So that means that the smaller series converges by comparison. So sum n over n cubed plus 1 converges, and that's by comparison. Well, we already stated our test here. Okay, so that's 11. Let's take a look at 12. Here we got polynomials again, and so I'm going to do some dominant terms thinking here, and this looks like this should be sum of n squared over n cubed, the two highest powered terms, n squared over n cubed. And if we cancel here, that's the same as sum 1 over n, which diverges. Okay, and again, diverges by the p-test. That's the harmonic series. So I look at this and I think this diverges. So since we've got a plus 1 on the top and the bottom, I'm not going to try a straight comparison, but I would do a limit comparison. And I'd compare it to the 1 over n. So you want to do the limit as n approaches infinity of your original n squared plus 1 over n cubed plus 1 divided by what you're comparing to, 1 over n. And I'll let you double check the details. This limit turns out to be 1, which is less than infinity. So they both have to do the same thing. Since this diverges, then this one diverges. So you'd want to go through and state your conclusion like we did here. But here I'm just trying to hit the highlights here. I'm not going through every single little detail with these problems. Okay, here I see a power on the top. I see an exponential on the bottom. That's begging for a ratio test, and we know that n cubed here is much less than 5 to the n. So this should go to 0 very fast, much faster than 1 over n. So I think this converges. and we're going to use ratio test because we got powers and exponentials. And remember, with ratio test, you do L as the limit as n goes to infinity, and we do n plus 1, the n plus 1 term, so this would be n plus 1 cubed over 5 to the n plus 1, and then divide by n cubed over 5 to the n. So if you invert and multiply on this guy, if you let me just kind of back up and do this in the same step, so times, and I'll invert this, 5 to the n over n cubed. Then this 5 to the n cancels all of these guys off except for the 5. And if we FOIL this out, it's going to be an n cubed polynomial, and this is an n cubed polynomial. So our dominant terms are going to be n cubed on the top and then 5n cubed on the bottom. So I'll let you double check the details, but this limit's going to be 1/5, which is less than 1, and that's going to converge absolutely. Okay, number 14, I look here and I see that -1 to the n, so I'm thinking alternating series test. But let's see what this is approximately equal to. So let's see, if we just take the 1 away, just look at our dominant terms, then this thing looks like sum -1 to the n over square root of n, which is sum -1 to the n over n to the 1/2. And if this was not alternating, it would diverge because 1/2 is less than 1. But since it's alternating, all we have to do is test that your b sub n goes to 0. So your b sub n is 1 over square root of n, and that does go to 0, and it's decreasing. Sorry, we need to check both of those things. So this is going to be alternating series test, and we've got two conditions to check. We want to check the second one first, which is that the limit of 1 over square root of n as n goes to infinity, that equals 0, and I think that's pretty clear. And then the first one, that the sequence is decreasing, and here I think we can do a ratio of I think we can use the ratio here to check that it's decreasing. So bn plus 1 over bn. So this is going to be 1 over root n plus 1. Oh, I'm sorry, we need a plus 1 in the denominator here. Because I was looking at this series, we need to be looking at this one. But you know what? We put a plus 1 down there, 1 over n plus 1. As n goes to infinity, that guy still goes to 0. And if we put n plus 1 in here, plus another 1, that'll be n plus 2. And then we divide by bn, which is 1 over root n plus 1. So if you invert and multiply, then this guy will come up to the top, and this will go down to the bottom because that's 1 over root n plus 2. So we'll have a root n plus 2 on the bottom, and a root n plus 1 on the top, and that's less than 1. So it goes to 0, it's decreasing, so this guy converges. Alright, let's look at 15. So I look at this, and right away I see that log n, and I'm already thinking integral test. And then I see a 1 over n, and derivative of log x is 1 over x. And I think we looked at one similar to this in the homework. So we've got a 1 over n on the bottom. If it was just some 1 over n, it would diverge, but we've got a little extra. So this goes, it goes down faster than 1 over n. But the question is it fast enough? So I look at this, and first thing I think is, hey, let's do integral from, this one starts at 2 to infinity. And let's look at 1 over x square root of ln x dx. And then we want to do a u substitution here. So let's let u equal ln of x. And then du will be 1 over x dx. So this is going to be integral from, plug this 2 in, log of 2, so ln of 2. And then as quote unquote plug infinity in here, log of infinity is infinity. Okay, if you'll loosely let me write infinity as a number. We could change this to the limit and then change it back, take the limit out and change it back if we wanted to. And then what we've got left here, the 1 over x dx, that's our du. And then 1 over square root of u. So this is going to be 1 over root u. And that is the same thing as u to the 1/2. So 1/2 is less than 1. This diverges. We don't need to find the value of it. We know it diverges by p-test. Okay, so this guy diverges too. Okay, this is interesting. We got log n divided by 3n plus 1. Alright, well let's see. As n gets bigger and bigger, our dominant terms on the inside are n and 3n, which is polynomial on the inside. So this thing looks like the sum of natural log of n over 3n, which is just going to be 1/3 on the inside. So this thing looks like summation of a constant, log of 1/3. And that's going to be infinity. You add up a constant infinitely many times. So we want to show that this is infinite, that this becomes infinite. So, well, if you want to show something diverges, one way to do that is divergence test. So let's think about, this is the general term, does it go to 0? So if you just take the limit as n goes to infinity of natural log of n over 3n plus 1, then by dominant terms, that's going to equal the limit as n goes to infinity of natural log n over 3n, and then these guys cancel, leave a 1 up on top, log of 1/3, so this is natural log of 1/3, which is not equal to 0. Okay, so the terms don't go to 0. This diverges by divergence test. Okay, so because this inside doesn't go to 0, so log of something that's not 0 doesn't go to 0. Okay, 17, I see this cosine 3n up on the top, and it's not an alternating sign pattern. This is always between -1 and 1. So what we want to do is we want to overestimate it. But, at most this is 1. So, just if we look, do our dominant terms type thinking here, the biggest the top can be is 1. Okay, so we'll overestimate the top. And then on the bottom, the dominant term is the exponential, the 1.2 to the n. And then 1 to the n is the same as 1, so you could write this as sum of 1 over 1.2 to the n. And this inside is less than 1, and it's an n power. This is a geometric series. This guy converges. Okay, so I think this converges too, because this is an overestimate. So what we want to do is we want to look at the absolute value series and show it converges. Okay, so we're going to look at the sum from n equals 1 to infinity of absolute value of cosine 3n over 1 plus 1.2 to the n, and take absolute value of the top and bottom separate. So it's going to be sum absolute cosine 3n and over 1 plus 1.2 to the n. And then let's see, we can do a direct comparison of this So we can overestimate the top with a 1. We can do comparisons and get back down to something like this again. So let's see, absolute cosine 3n over 1 plus 1.2 to the n here is going to be less than or equal to, we'll increase the top to a 1, because the biggest this can be is 1, and it's always greater than 0 because the absolute values. We got 1 plus 1.2 to the n. And then we'd like it if we could just get rid of that 1. If we take the 1 away, that makes the denominator smaller, so the fraction gets bigger. So this is actually less than equal to 1 over 1.2 to the n. And so by direct comparison, we actually got this guy here, which is the same as this. That's geometric. It converges. Okay, so then we would end up here by saying, since the sum of this one converges, the sum of this one converges, that is, the sum of the absolute value series converges, so then the original one does too. And that's by comparison test. So this is direct comparison. So I didn't state I stated the conclusion, I didn't write it out. I'll want you to write out the actual conclusion. Here I see an nth power there, I see a 2n power there. I'm thinking root test here. And just to kind of get an idea of, whether or not this guy converges. Let's see here. We could write this as 2 times n. That's the same thing as n squared to the n power, because 2 to the n. I'm sorry, 2 times n would be 2n. So now we got nth powers on the top and the bottom. So this actually looks like I need approximately equals to here right now. This is equal to the sum of, these are both n powers, so we can put them inside the same nth power. So n squared on the top, and then 1 plus 2n squared on the bottom, and then nth power. And then that is approximately equal to dominant terms on the inside. N squared over 2n squared will be, the n squareds will cancel. You have 1/2. So this looks like sum of 1/2 to the n in the limit. And this converges. Okay, so we're going to use a root test on this. This converges because it's geometric. So in the limit, this thing that needs a root test, it looks like a geometric. So we're going to do root test, let L be the limit as n goes to infinity, and we're going to do the nth root of the absolute value of this thing, but if n is positive, this is all positive, so we really don't need the absolute values. So n squared over 1 plus 2n squared, all nth power, these guys cancel. So now you're doing limit of n squared over 1 plus 2n squared, and that's 1/2, which is less than 1, and converges. Alright, let's move this on down. Ooh, we're getting to some interesting stuff. Let's see, 1 times 3 times 5 all the way up to 2n minus 1, which is some odd number. And then on the bottom we got a 5 to the n and an n factorial. Okay, an n factorial is 1 times 2 times 3 times all the way up to n. Okay, and this goes up to 2n minus 1, but if you look at the numbers here, the even ones are left out. Okay, and so the even ones would be 2, 4, 6, 8, 10, all the way up to 2n. So there's only n factors up here. There's also n factors down here. So let me see here. I think let's overestimate the top with the missing factors here. The missing factors are 2, 4, 6, all the way up to 2n, like that. And so 2 is bigger than 1, 4 is bigger than 3, 6 is bigger than 5, all the way up to 2n is bigger than 2n minus 1. So I'm going to do a direct comparison here. This would be less than or equal to sum 2 times 4 times 6 all the way up to 2n over 5 to the n factorial. Okay, now the reason I did that is because I noticed I got a common factor of 2 here, and if I pull that 2 out on the top, then I'll have left here 1, 2, 3, all the way up to n. So 1 times 2 times 3, all the way up to n. And on the bottom I've got my 5 to the n factorial. But that's what this is right here, n factorial. So those guys cancel out. And now that equals the sum of 2 over 5 to the n, which converges, because this is the sum of 2 times 1/5 to the n. Just pull the 2 off in front, and then 1 on the top is the same as 1 to the n. So 1 to the n over 5 to the n is 1/5 to the n. So this converges because it's geometric. So let's see here. So direct comparison, we know this one is less than this one, which equals this, and we know that that converges. So this is just going to be a comparison test, a straight comparison. But you had to be a little bit clever about it. Okay, so since this bigger series converges, the smaller one will too. Okay, let's see, 20, let's see, nth power is here, but then an n squared. So we got some exponentials, we got a power function, and it got a negative out in front. We could break the -5 up into -1 times, oh, you know what, no, this is 2n power. Okay, so that's an even power. Anything to an even power is going to be positive. So this is the same thing as if we did 5 to the 2n up on top. And then n squared, 9 to the n on the bottom. And then let's see, let's write the top as a power to a power. So this would be sum 5 squared to the n. And then on the bottom, n squared times 9 to the n. So let's see here. So that's the same thing as the sum of, on the top, 25 to the n power. And on the bottom, n squared, 9 to the n. So we've got an exponential on the top and an exponential on the bottom. The exponential on the top is bigger. So I tend to think that's going to pull this thing up to infinity, even though the bottom exponential is multiplied by an n squared. Because the exponential should win out. But we've got exponentials and power functions, so this is going to be a ratio test. So that's pretty clear here. And we could have gone right to the ratio test with this one, and it would have got rid of that negative, because it would have canceled out. But L then is going to be the limit of the n plus 1 term, so that's going to be 25 to the n plus 1 over n plus 1 squared, and then 9 to the n plus 1, and then divide by this, which means multiply by its reciprocal. So if you'll let me in the same step, n squared 9 to the n comes up on top, and 25 to the n on the bottom. So this is going to cancel out all of those except the 25. This 9 to the n is going to cancel out all of these except 9, the 1 9. And so we've got left 25 ninths, which is going to be 25 ninths. And then we've got n squared over n plus 1 squared. This is n squared plus 2n plus 1. So if you look at dominant terms, n squared over n squared, that's going to be times 1 in the limit. But this limit is 25 ninths. That's greater than 1. So this is equal to 25 ninths. which is greater than 1. So there's a little bit of algebra that I left out here, foiling this thing out and then looking at the two dominant terms. But the 25/9 that is left, that's what matters. And if it's greater than 1, diverges. Okay? So, and that's kind of what we thought here. This bigger exponential would win out over the smaller exponential, even though that's multiplied by an n squared. So the top gets bigger faster, diverges. That was kind of my feeling. All right, let's see here. Got another alternating series. Got a root n over n plus 1. So if we look at dominant terms, this is equal to sum -1 to the n minus 1. And then we'll do root n over n, which this is n to the 1/2 power. This is n. So that's the same as sum -1 n minus 1, and then this would be 1 over square root of n, or 1 over n to the 1/2. Okay, because you can think of n as root n times root n. You can cancel those and get 1 over root n. And let's see, this is an alternating series, so I'm thinking alternating series test. And this definitely goes to 0, and as n gets bigger, this will decrease. So I expect the same thing will happen here. So I think this converges. So your two steps here, again, are going to be to look at the limit of the general term, that root n over n plus 1, as n goes to infinity. And again, by dominant terms, it's 1 over root n, so that's going to be 0. And then the first condition is to check that this guy is decreasing. So if we did a ratio test here, I don't think a ratio is going to help us. So if we did a ratio, we do a root n plus 1 divided by n plus 1 plus 1, so it'd be n plus 2. And then it would be, the whole thing would be over this term. Okay, so, well, that's going to be the same as if we just invert and multiply there. So if you let me do this in the same step, it's going to be times n plus 1 will come up to the top, and then the root n will go down to the bottom. And yeah, we did run into a problem here, because these two we can group together. So this is root n plus 1 over root n times these two, n plus 1 over n plus 2. And here the top is bigger than the bottom, so this is greater than 1. But here the bottom is 1 bigger than the top, so that's less than 1. So we want this whole thing to be less than 1, but we can't tell from the way it is there. So I wouldn't use ratio test. I would not use a ratio on that one. So I would look at the derivative test. So let f of x equal square root of x, or x to the 1/2 if you want, divide by x plus 1. And then you want to show that f prime of x is less than 0. And you'll just have to do a quotient rule from, let this be your f, and this guy be your g. So f prime g minus f g prime. And that derivative should end up being less than 0. And number 22, I don't like these two things that are subtracted up on the top there. Because as n goes to infinity, n plus 1 and n minus 1, those are basically getting close to each other. So this top here is looking like infinity minus infinity. They're both becoming infinite, but they're really close together. Like if you put, if you put n equals 1,000 here, this is root 1,001. This is square root of 999. So those are going to be pretty close together. I think, if n equals 0, This is root 1 minus root 1 is 0. Well, n starts at 1. Root 2 minus root 0, so square root of 2, which is 1.7. And then I think they get closer together after that. But I know what they want you to do here, and it's really messy. We want to try and get rid of this infinity minus infinity on the top here. And the way that you do that is by multiplying by the conjugate. So you would take this whole thing and you would multiply the top and the bottom. So let me take this guy and just bring it down here. And what they want you to do is take and multiply the top and the bottom by the conjugate. So we're going to take 2 copies of this guy. Except we want a plus sign right here and right here. And then when you do that on the top, what's going to happen is this looks like a minus b, a plus b, which is a squared minus b squared. You'll get rid of the square roots. And on the bottom, you've got a sum of 2 things. So as n goes to infinity, the sum is infinity plus infinity, which is infinity. So that's getting bigger. Whereas at this point, you don't know what's going to happen because it's indeterminate. So, and then once the square roots cancel out, the top will be really nice. So, but that's probably a little too messy for a test question. So, okay, well, this list is by no means all inclusive, but hopefully, helping you kind of talk through some more of these is adding to your intuition and giving you some better ideas of how to start the test. And again, here actually I did more here than you would need to do for the first test questions, where you just have to tell converge or divergent which test. So like on this first one, you would just stop after comparison. So this would be your answer if it's a short answer question. And then if it's the back page of the test where I have you work everything out, then you'd have to include actually working out the test. So this is your intuition here. Okay, that's the front side of the test. Same thing here, like on number 12, this is your intuition here. Okay, and you're done. But then if it's the back of the test to actually have you work it out, then you'd have to work out your limit, show me all the details in here, and then state your conclusion that you're using a limit comparison test. So, okay, very good. Hopefully this was helpful to you.